So you want to learn real math, despite everybody asking what you're going to do with a math degree and all the software engineers making more at their internships than you ever could with a master's or PhD in pure math, and the applied math chads making fun of you for thinking knowledge is its own reward. Despite all of that, you decided to study math anyways. Whatever masochistic complex brought you to this moment, we're going to do math together. It won't be fun, you won't like it, and if all goes well, you might get hired as a high school teacher. So you're an undergrad that's just started their first proofs course, or you need a refresher because you're bored and you hate yourself. Or maybe you're a math hobbyist who actually has a very fruitful career in engineering, data science, or software development, and math just tickles you in all the right ways. No matter where you are, we begin at the same spot sets. Not those sets, or those, but these, and these. Think of sets like a box. Well, more like a magic box, but a box. Why is it magic? Because you can hold an arbitrary number of objects or elements of any kind in this box, but only in your imagination. Those are sets. We define sets in two common notations roster notation, which is literally listing out the elements, a problem when you have a lot of elements, and then there's set builder notation. Set builder is fun because you don't have to list everything, which saves time and money, and most importantly, insurance costs. To construct a set with set builder, you need a variable, a line, and a condition. The condition is like a guest list for getting into a club. Different clubs have different rules for entry, so different elements belong to different sets. So let's say you like even numbers and you hate odd numbers because you hate the idea of yourself being odd and you're projecting your feelings onto the numbers. You can make a set of even numbers that you wouldn't write explicitly because there's a lot, like infinite a lot. So we say we're letting in the elements such that they are divisible by 2. Now we're building sets and making friends with numbers in our new club because you're lonely and your friends will always be numbers and no one else. So what about sets interacting with each other? What if sets themselves want to mingle? I don't know. They have active social lives. Two sets union, which is creating a set containing all the elements in both sets. They can intersect if you just want what they have in common. We could look at containment, where we see if all the elements in one set also belong to the other set, where one set is literally inside the other set. Gross. And there's complementary sets. They're the evil clone of the set, but opposite in every way. They contain all the elements that are not in the original set. And visually, it's like this. Notation wise, we write this. Now, some sets are special, and those sets are the empty set, N, Z, Q, R, and C. The empty set is self explanatory. It's an empty box, just like the box containing my hopes and dreams. We denote it like this. N is the set of natural numbers. These are the ones you use to count. If you're piano, your nested empty set BS is in Q and 0 is not a natural number. Z is the collection of integers, so now we can associate our negative feelings to negative values and associate them with 0 when we feel the numbness of the void. With this void, specifically between numbers, we have to find a way to associate values with those in-betweens. Enter the rational numbers, or collection of all integer fractions. Unfortunately, this set isn't complete because we failed to acknowledge the voids within our voids. Thus, we philosophically divert to chaos and irrationality, which is why the ancient Greek mathematicians went crazy over finding a fraction to represent the square root of 2. Since Q is that unreliable friend that's always asking for rides and does nothing but steal oxygen from you, you need more reliable friends that will pick up where Q left off. That's R, aka the real numbers, aka the friend that always brings Stella instead of PBR. Now, a square root conundrum doesn't stop with R, because some asshole decided it was alright to take the square root of negative numbers. This, of course, gave us the imaginary unit I, and eventually the set of complex numbers, which can be described as a set of ordered pairs with special operations, or as a linear combination of real and imaginary units, A plus BI. While sets might be nice to look at, we have to consider why they're important to mathematics. Because let's face it, they're not important in many other places. Understanding the axiomatic principles and foundations of mathematics will not give me the knowledge to help me do my taxes. Some of the most profound theorems are those where we attempt to prove that two sets are equivalent. Like perhaps the theorem that states the set of people that like the Kardashians and the set of people that have an IQ less than 80 are in fact equivalent. The typical proof strategy for defining when sets are equivalent is by proving that both sets contain each other. In other words, proving that all the elements in one set belong to the other and vice versa. We let X be an arbitrary element in the first set and show why it must be in the second set, and then do the same to an arbitrary element in the second set. This same technique can be used to prove relationships for a sort of set algebra, or more accurately, a Boolean algebra, where the operations are unions and intersections. As an aside, another typical operation is taking the Cartesian product of two sets. This gives the set of all possible ordered pairs that contain the elements in the first set in the first position and the elements of the second set in the second position. For example, Z cross Z would be the set of all integer pairs. If A is the set of words failure, loser, and hypocrite, and B is the set of words void and dread, then A cross B looks like this. Hopefully you now have a better understanding of sets and why they're barely useful. If you like this video, Take the time to like it and share it with your math friends and see if they get a kick out of this. Otherwise, thanks for sharing your time with me.